we're going to discuss quantum computers and quantum mechanics, and then investment in quantum tech, but that will be this afternoon. This will not be what I consider a light discussion. It will go fairly deep. We want you to be able to understand quantum computers and quantum mechanics a bit, so you can at least talk at a reasonable level and understand what people are talking to you about. It's not going to be easy, but you will have all the slides and unfortunately not a transcript at this time. This is a follow-up boot camp to my previous boot camp on advanced AI systems, which I personally have more hands-on experience with, as I do not build or design quantum computers. Mea culpa. You will, however, in the lab portion, build quantum algorithms on a quantum computer simulator. So just so you can say you did it and you've done it, and I don't know, maybe I get to score you some points somewhere. Quantum computers are fundamentally the same as classic computers in that you take input and use representations applied to physically existent low-level binary states to process data. They reside on a binary state foundation. Like classical computers and the entire universe, that is positive and negative charges. But that's where the similarities end, because quantum computers use superposition states, unlike classic computers, which have only two binary states. And quantum computers take far more advantage of more advanced properties of that foundation, including the notion of existence in multiple states at the same time, and in correlation. So superposition and entanglement is what we're talking about. As a result, they are massively faster than classical computers for certain types of processing. They are currently far slower for other types of processing, so far. What you need to understand now is where they are faster and where they're slower, and how that translates into real value now and in the future, if you're going to invest in this stuff. Quantum computers use quantum mechanical phenomena to run. And that may seem complicated, and it is, to some degree. It's the behavior of subatomic particles, like electrons and photons, and even deeper into quantum mechanics. More importantly, the waves they emulate and perpetuate. And we'll talk a lot about waves later on in the presentation. But why do we even do this? Like, why bother with quantum computers? And the answer is speed. Massive speed from simultaneous parallel processing, with far less resources and frankly far beyond the physical abilities or limits of classic computer systems. But why speed? What do we need speed for? Well, the answer is artificial superintelligence. You can say general intelligence, but I'm going even beyond that. Superintelligence, deep layered, multi-dimensional context of the kind we humans use each and every day. Same stuff. And that's why we need speed, to stay, and of course, to stay ahead of the other guys. Because if the other guys get the speed, well, then we're going to fall behind. Dimensions are where the hidden world of solutions and innovation lies. We can't see this stuff very well with our limited three-dimensional human perception and cognition. We require a little bit more help because it requires massive increases in resources or new innovations like quantum computers and cognitive AI. These machines generate new ways to look at our world, and frankly, looking around our current world, we humans can use the help. I mean, that's pretty obvious, isn't it? So how do these things even function? Well, quantum computers use the states of quantum particles, means the subatomic particles, which exhibit consistent behavior. And it's important that the behavior is consistent, because if you're going to use a computer, you're going to want that type of behavior to persist. And quantum computers overlay representations of those states to a qubit. That's a bit controversial. We'll get into that later too. Now this is similar to how a bit in a classic computer represents the on-off state of a transistor by measurement of the output voltage. So we're basically setting these states in quantum computers and we're measuring the state. It's the same in a classic computer, except we're using a transistor and the output voltage of that transistor to measure the state. Is it on? Is it off? In a classic computer, we apply a logic gate to the bits to represent the real world. So this is like data, like numbers and processes and streaming video and TikTok and whatever else. In a quantum computer, it uses quantum gates, and they are applied to qubits to do processing. Well, not video, at least not yet, possibly never. We just don't know how far these things can go and what they can do. But most likely that quantum computers will be like supercomputers. Okay, nobody carries around a supercomputer. Well, we do now, but nobody carries around the new supercomputers. They're too big. They sit in the cloud infrastructure background. And that's probably where quantum computers are going to wind up, somewhere in the infrastructure. Oh, you'll still use them. They'll, the results will show up on your phone, but they're basically going to be sitting in big places because they're fragile. Quantum computers measure quantum particle states using various detectors and various methods. And quantum computers need things to do this, like supercooling and superconduction, lasers, microwaves, complex detectors. There are no garage builds yet, but quantum computers have immense value, especially as an infrastructure component. So quantum computers have quantum particles trapped inside a quantum processor that are manipulated by sending signals to a control mechanism, i.e. microwaves, lasers, etc., that instigate and change and read the states of these trapped quantum particles as qubits. Same as applying power to a transistor in a classic computer, sort of the similar mechanism. We talk to these control mechanisms through qubits and quantum gates using representations, and we'll talk more about representations later. Humans we're just starting to poke around in the quantum world, where dimensions of existence behave similar to particles. These are dimensions we have trouble comprehending, such as the interactions of quasi-particles, but this is advancing. We are getting better at this stuff. We're learning more. The control mechanisms use special quantum algorithms and now program languages that are still in development but will soon come out that will allow us to communicate a little better with these things. Essentially, we are today at the machine code stage of quantum computer development compared to the development life cycle of classic computers. So we're sort of like in the 1960s of classical computer development in quantum computers today. We have a very long way to go, but quantum computers are in use now, and they're having an impact, as you'll see. Mostly right now they're being used for research in cryptography, finance, big pharma, and by very big orgs who can pay to play. These things aren't cheap. This diagram represents a very general and simplistic view of a quantum computer. On the right, real-world data or problems are captured by an application code, and that data is encoded specifically for a quantum computer, or the act of converting or representing real-world data. Now, quantum gates are applied by the app to the qubits to instigate particle states that then represent the real-world data. Quantum controls, this is where the physicists play, are implemented to impact or measure these states. Hardware controls, and this is where the engineers play, are used to set the particle states. The arrows on the diagram aren't flows as much as they are relationships. We set data via the gates, we instigate change, and read the results. The only thing flowing is a very small amount of electromagnetic radiation in the controls, and of course the particle waves. The states are changed by the gate, and the data is then presented back for real-world analysis or output to a classic computer. This entire structure requires quantum developers and quantum data scientists, mathematicians, physicists, hardware engineers, and all the support staffs around them. But you can access a quantum computer online with just devs and data engineers. And this access will soon grow in the cloud. Quantum control layers, again, this is where the physicists play, include things like pulse digitizers and signal schedulers, etc., etc. And none of this stuff is overly complicated. I mean, the math is complicated, but the rest of it is something that we can sort of all learn and pick up. Quantum computers detect particle states through the use of detection mechanisms like ion traps and superconducting circuits, etc., etc., etc. Now, superconducting circuits are often conflated as qubits, but there is a bit of a differentiation between the two. Same mechanisms are also used to instigate states, so not only measure, but instigate. And one example of this is a microwave cavity, which is a superconducting structure that traps quantum particles and controlled microwaves together. And this causes an increase in the frequency of waves from an excited particle. And then the system uses an amplitude, or an amplifier rather, to detect the wave and infer the quantum state of the particle. But all these states are very, very fragile. They're not robust enough to carry in your pocket yet. So we have particles in some state, and the quantum computer both controls and reads or measures the states, using both quantum controls and physical controls. Quantum controls, again, are the signals and pulse controls, and this is the nature of that system. And you can think of this all a bit like a concert, where you have performers who are going to perform on a stage, and they're going to send sound waves. They're going to produce sound waves that are then going to be carried and delivered back to an audience, and the audience is going to hear those sound waves, and they're going to interpret the information in their own head. So in between the two is going to be a lot of different components. There's going to be people who build the stage and people who run the electrical power to power everything. There's going to be people who are going to be setting up and managing equipment like the soundboards and the lighting systems and the pyrotechnics. And then you're going to have a whole bunch of people come in and sit down at those boards and turn the little buttons and adjust everything and make it all go. And then you're going to have the performers come on stage who are going to produce the waves that are then going to be amplified out to the audience. The audience is going to hear those waves in their head. They're going to interpret them. and they're going to enjoy it, they're going to hate it, whatever. Effectively, that's a quantum system. It's probably the best way I could describe it. So other methods for detecting states include electron sensors for detecting the state of electrons, like a quantum dot. Now, a quantum dot is a charge sensor. It's used to detect and measure particle state wave instigation. So it's electron changes from a particle that are inside of something like a nearby capacitor, which is then detected by a dot, a quantum dot that's placed nearby the capacitor. So these dots are very, very small semiconductors that trap and contain electrons in such a way that their energy levels can be measured and used for quantum processing. Another method is called a topological qubit, and this uses properties of other matter, like quasiparticles. And when you start talking about quasiparticles, you start talking about another dimensional layer inside of quantum mechanics. Quasiparticles are not physical particles. They are what are called a collection of excitations of quantum particles. Now, excitations are changes or variance in those quantum particles. So this is where we start to get into this dimensionality. If you start to think about the real world and how you can put it into something like this type of dimensional system, then we start to get to more advanced dimensional concepts similar to our own cognition, where we can think of quite a few dimensions of context at once. Now, the variance in behavior of exotic quasiparticles like phonons or excitons or plasmons, polaritons, magnons, etc., etc. The processing is used by the topological qubits as state. So they look at these things and they say, aha, we can determine a state. So we talked about qubits, so let's touch briefly on memory, because computers have processors and they have memory. Quantum computers, or quantum computer memory, is known as QRAM. It is consistent with classic computer memory in that classic computer bits are stored in RAM and long-term memory, and in a quantum computer, qubits, or their state representation, are stored in QRAM. Now, we should bear in mind that real quantum states, like the quantum states of particles held in suspension, are very, very fragile, unlike bits and transistors. The same general sandwich for both quantum computers and classic computers exists. We have transistors versus particles. We have transistor change versus particle state manipulation, bits versus qubits, logic gates versus quantum gates. They use the bits and qubits to cause, physical mechanisms to instigate or measure transistor state change or particle state change. This is all very consistent between the two systems. The difference is a quantum computer has a superposition and entanglement states. That's additional dimensional layers. To get information or real-world data into a quantum system, this is pretty critical. We need to encode the info into a quantum computer state. Now, this is known as quantum state preparation. And we do it by applying quantum gates to qubits. And then you can add the state, the qubit, to a QRAM, theoretically. States are very fragile, subject to outside interference, including even like radio waves and other waves and neutrinos and things from space. So this whole thing of QRAM is hypothetical. It is only in the research phase. I would say it's a little even before that. It's in the whiteboard design stage, but the goal of QRAM is to persist quantum states in a quantum system. Okay, so let's step into the qubit swamp. I hate going here. A lot of people are going to have difficulty understanding what the heck is the difference between, a qubit and the state of particles. Like, they get it that there's a particle state, and they understand this qubit sort of represents that particle state, but they really have a difficulty understanding what the heck is the difference between the two. And that's where you'll get into a bit of a debate. So I'll mention the debate because it'll be pitched to you, and you need to come up with your own rationalization of what the heck we're talking about. So a qubit is a logical representation of a two-state physical quantum system. Physicists will demand they are 100% physical, such as a loop of superconducting wire that can flow current in two directions. And they'll say, that's a qubit. And you'll say, the wire? And they'll say, yes. But in your head, you'll be going, yeah, but qubit, wire, two different things. That's a superconducting wire. That's not a qubit. What's a qubit? Others will see the qubits as representations of state to sort of solve this issue. Now, the closest analogy you can sort of come up with is an electrical circuit. I mean, you can't really hold an electrical circuit in your hand. Well, you can. You might get electrocuted, but you're not holding the circuit. What you're holding is the things that make up the circuit. Those are the physical things that make up the circuit, but the whole thing together is described as a circuit. Is that physical? Well, I don't know. It's not physical by nature, but it describes physical elements and the behavior of the system. So another way to consider qubits and particles as co-attached dependent entities. You can't have one without the other in a quantum computer sort of thing. And that's another way some people consider it. Now, I personally view qubits as real-time representations of the state of underlying physical particles. All of this is how qubits relate to quantum particles. It's probably, I'm just going to recommend, it's easiest to just think of qubits and their quantum particles as the same thing. And then you get out of all this stuff. So this, what you see on this slide, is the crux of the issue. Because of the relationship between physical quantum systems and the real world. A qubit is the crossover point between these two realities. Same with a bit in a classical computer. Qubits are physical manifestations of our perception applied to the context of a quantum system through quantum gates. They talk directly to the physical control and measurement systems in a quantum computer that interact with the quantum particles and their behavior. Quantum gates are logical structures applied to qubits to affect a change in the overall state of the system. The gates are not physical, but they directly control physical reality at the quantum level. Quantum circuits are one or more gates. Now, quantum gates are something that are called unitary transformations that act on qubits. These unitary transformations are mathematical operations that describe the dimensional variance in a quantum system, i.e., changes over time. And they are reversible without any loss, not unlike logic gates in a classic computer. So this now is a sample of code from a quantum algorithm. The circuit contains the gate, which is comprised of two qubits. The gate is just one or more coded control instructions applied to one or more qubits, similar to how logic gates are applied to bits. These things are the building blocks and the control mechanisms of the representation we call quantum code or algorithms. Qiskit, in this example, is just an IBM quantum algorithm library that includes a quantum simulator, so you don't need a quantum computer to run this. It sort of pukes out the same results, as it were. Now, this particular code snippet implements 2 qubits. It applies a type of gate called a Hadamard gate. That's French. If it's English, you'd probably say it Hadamard. It was Hadamard gate, which is a structure that creates a superposition of all possible states for the qubits. Then the quantum computer uses the output or measurement to do other processing. So what we're talking about here is very, very machine code-like. We structure data and then alter the states to get the output, just like the old machine code days when you'd go in and, structure the data so it would flip the switches in a certain way. And yes, that was all before my time. So I don't know what I'm talking about with basically with old machine code. The best I did was I've handled a couple of punch cards, but as a kid, but that was about it. Okay, quantum computers take real-world data and they use quantum particle states to process data far faster than current classical computer systems. And this allows humans to apply and use more data and far more complex representations of the real world to solve deeper problems and create deeper innovations, such as drug compound research or new materials. Even more powerful in these systems is the ability of advanced AIs to feed or use far more dimensionally complex data and representations of the real world, including some that humans either can't or are unwilling to perceive. So we know our AIs can go deeper in terms of contextual understanding. And that's where these types of computers can come into play, because to understand deep layers of context takes a lot of power, a lot of processing power, a lot of what they call compute. These systems give us hope for that. The hope of a quantum computer is due to their capacity for speed applied to these deeper contextual dimensions in artificial comprehension. So you can imagine using ChatGPT, and ChatGPT has some measure of context. It's pretty crude and rudimentary context. It's nowhere near as advanced as human context, but it will get there. It needs an awful lot of power to do so. This is the type of mechanism that can get us there. So right now, we can factor numbers very, very fast. This is the whole, foundation of encryption. But in the future, this could be used to comprehend or learn fast-flowing context. And we're talking about mass-flowing context over time, dimensions with fewer resources like similar to human cognition. So what this is called cascading deep context. You can think of this as if you're out having a drink somewhere and somebody says something and you reply back to them with a sarcastic comment and everybody gets it and laughs, and that's sort of that deep, flowing, cascading context. Okay. At this point, we're going to have to stop with the quantum computer side of things, because we have to take a look at the foundation that underlies all of this tech. Quantum computers are built on a foundation of the physics of quantum mechanics. So that's where we're going to go next.